Good afternoon, everyone. I hope everyone's still awake. I'm going to give you a brief overview of the project called IMAGE. In long form, it's called Impact of Agricultural Emissions on Rural and Urban Air Quality. Now, today you heard a lot about primary emissions of particulate matter, meaning directly from source to the atmosphere and back again. So IMAGE actually focuses on secondary production, meaning through reactions in the atmosphere of certain components, particulate matter is formed, and we still see the effect of it. So we're going to take a step away from the conventional of what we've seen and step into the realm of a bit more mystical atmospheric chemistry of reactions in the atmosphere. So just to give you a little bit of background of why it's actually important. So we know that clean air is a basic requirement for human health and well-being. WHO has recognized this and has given many a quote over the years, especially of late. According to the WHO, approximately 4.2 million premature deaths occur worldwide as of 2019, with 99% of the world's population living in places where the air guidelines aren't met. Now, this is not news to anybody who has been listening to the presentations this morning. Contaminants such as particulate matter increase health concerns such as strokes, heart disease, as it was mentioned this morning, lung cancer, and both acute and chronic respiration disease, including asthma. Secondary production of particulate matter from sources such as ammonia, from formation to concentration and composition effects, must be understood in order for us to understand how secondary particulate matter production actually occurs in our atmosphere, especially since the components of secondary production can be as high as 90% in the atmosphere. And this is one of my favorite graphics when it comes to this because it just demonstrates an inhalation. And when it comes to particulate matter, how far that inhalation can travel. So as we've seen with the communications panel, imagery is very important. And this is one of my favorites for showing just how vulnerable we actually are to these microscopic particles. The second image, and I invite you to take a very deep breath because I can guarantee you this will be your last one for a while, is also one of my favorites. So this is a world map that NASA has produced, and it's a way of visualizing what particulate matter looks like, what aerosols look like. So as we heard, this focuses on primary emissions. The blue indicates sea salt, the red indicates black carbon from wildfires, and the purple is dust. So you can see the Saharan dust traveling over Africa. You can see the wildfires from North America traveling actually over Ireland. And this image really shows how particulate matter does not recognize any boundaries in the world. It does not care about borders. It does not care about oceans. It is literally in every ecosystem in the world, and you cannot escape it. I guarantee you, looking into this room, you're thinking the air is beautiful and clear. Truth is, you're inhaling millions of particles as we speak. And the most favorite analogy that I developed over the years for students especially, because they always have trouble visualizing all this, and they're like, why should we care? Why does this matter? My best example for them is always, go to the beach. It will break down the physical barrier, because I guarantee you, you will not only see the sand blowing, it will be in your mouth and your eyes. And that is the physical breakdown of how particulate matter works. It's within what we breathe. It's within our life, and we can't escape it. So just to finish off the background, currently the largest source of ammonia, which is one of the biggest contributors to secondary particulate matter, secondary aerosols, is agriculture, which also produces about 99% of emissions, as you can see from the graph. It's the biggest contributor, mainly because of fertilizer use, slurry use, etc. We all know why they're the biggest contributor. Agriculture is also the leading land cover type in Ireland and is one of the key industries with practices capable of reshaping biogeochemical cycles, such as the carbon cycle, the nitrogen cycle. Additionally, Ireland's agriculture emissions exceed 30% of total greenhouse gas emissions. And due to the nature of the relationship between ammonia and particulate matter, by mitigating the key primary component, ammonia, we can actually take a handle on the secondary component, particulate matter, because the less of the primary you have in the atmosphere, the less there is to react. So basically, this would also allow us to comply with current directives in place. And also, January 2023, Ireland has received an infraction notice from the NECD due to ammonia being too high in the atmosphere. So it is extremely important to reduce these pollutants. So what do we actually do with the image project? We try to determine how agriculture impacts air quality in Ireland through the emission of ammonia and the formation of secondary aerosols, and we will build a model out of this to show how it actually works. So one of the things that we do is a long-term monitoring of a couple of sites in County Fingal, County Dublin, North County Dublin, for anyone who doesn't know where Fingal is. The image project is building on work carried out previously there, so we do have historical data, and we will build on that data with current monitoring to show what ammonia levels are present and also what particulate matter levels are present. And we will do ion analysis to determine the ammonia component of the secondary particulate matter, therefore producing data on this is the contribution. We are currently working with passive samplers, which are just samplers that sit on land, and we just collect the filters out of them every month, and we do this continuously over the life of the project. And we also work with active samplers, which have a pump running them, and they take in air actively through a pump, and they just collect the sample, and again, they are collected over time. Now, the analysis that we do then involves ions, so we use a technique called ion chromatography. The system, as you can see, produces beautiful graphs with lovely little peaks where they tell you, this is what you're looking for, this is how much of it there is. So it's actually a really beautiful system, it is very simple, and it produces a lot of data in a very efficient amount of time. So it's a very efficient piece of analysis, and gives us loads of information on secondary particulate matter. In terms of what else is on site, we also have weather monitoring at each of the locations. And the importance of those is, so this is wind direction and wind speed at one of our sites. And in terms of seeing it in the real world, so this is when we map it out, this is what it actually looks like. So getting this kind of weather data just increases our resolution and our precision when it comes to the model. It will tell us, okay, this way is the wind that goes. So if I were to reverse it, the flow would actually be a flip chart of this. So it tells me, okay, the most effective area that might affect my sampling is actually coming from northeast. And it's really important to know those factors in order to have accurate models. Similarly, this is just rain intensity and rain vectors. And this is important from a bed deposition perspective to see how ammonia comes back onto my site. What I'm measuring, this is the feedback loop that I'm seeing. These are the dynamics. And then this is just the sort of data that we expect also to have. So we have ammonia levels and the ammonium portion of aerosols. We also have the ambient concentrations at 3 different sites shown in the graph. We have the breakdown of particulate matter sizes, and then we have some extra meteorological data, so that's actually temperature data that you see in the far corner there. So this is the type of data that we're dealing with, and it gives us a lot of insight into how particulate matter dynamics work on our sites. And then the second part of the project is to look at a seasonal ammonia particulate matter monitoring, and this is actually an intensive campaign. So here we have high volume sampling for a 6-month period, where 24-hourly high volume filter sample collection will occur. And this high volume sampling gives us a higher resolution for the model and gives us a lot more information. So long-term sampling is great. However, you do need a high volume sampling impact at the same time. It just gives you more data, it gives you more resolution, and it also allows you for a nicer source apportionment model. So the site assessment that we went with was for the site Kilkit. It has been assessed fully. We assigned the entire geographical maps, had a look at what's around it, what could affect it. And then the data out of this will be compared with Malin Heath from Cannon Point and Claremorris, and then the temporal signals from air masses will be separated by consolidation with weather and atmospheric dispersion. And then just real quickly to conclude, so the source apportionment model, we're looking to estimate annual average and seasonal variation of atmospheric ammonia and PM levels in multiple areas with different densities of activity. And then the receptor modeling will identify and quantify sources contributing to both PM2.5 and ammonia. We're looking to use different meteorological models to supplement our dispersion models. And basically, hopefully, our main aim is to use these models in an Irish context for policy and regulation development in the end. Like, that's always the ultimate end goal, isn't it? So hopefully the model will be built with that goal in mind, and hopefully it will be used in the future. So yeah, if anyone's interested in any more of the work being done, we have published historical data and we have an extensive literature review on the topic already in the works, and it has been published. They can be found with the relevant DOIs. and I am happy to answer any questions.